invitation for delivering a talk in the John Conway Spirited Seminar Series. Mateusz is currently affiliated with the University of Konstanz, and he is going to discuss about enumerative geometry meets statistics, combinatorics, and topology. So a kind of area which is quite in fashion nowadays, particularly in algebraic statistics and the techniques in studying the data by using algebraic geometry. Over to you, Mateusz.
Thank you very much for the introduction, and thank you very much for the invitation. It's a great pleasure to give this talk. Indeed, it will be about interactions among quite different branches of mathematics, geometry, statistics, combinatorics, and topology. I often introduce myself by saying that I am an algebraic geometer by training, but a combinatorist by heart. So in particular, I very much like when answers to mathematical problems are very easy. And if we want to compute something in particular, I like when the answer is, let's say, a natural number, a positive integer. So let me start by presenting some of problems in those various disciplines, precisely when the answer is an integer. So the first problem is given a graph with the set of vertices V and the set of edges E. We would like to count the number of so-called proper colorings using K colors. So K here is a given fixed positive integer. And what is a proper coloring? Well, we just assign colors to vertices. So every vertex gives a number, let's say from 1 to k, and we require that two vertices that are joined by an edge do not get the same color. Then we call the coloring proper. By the way, I should have started with that. If there are any questions at any point, please do not hesitate to ask them, and I will try to clarify it. Okay, so when we are given a graph and the number k, the number of such proper colorings is some integer. It could be 0, it could be 5, 7, etc. So this is one kind of problems that I like, but there is maybe a better question to be phrased here, namely, how does this function that counts the number of proper colorings changes when we change k? And what is really nice and can be proved, for example, by induction on the number of edges, is that the answer is a polynomial in k. Okay, so we get a so-called chromatic polynomial of the graph G. That's one polynomial that, if we evaluate that polynomial on k, we precisely get the answer how many proper colorings there are. And one can say that maybe I left this word of integers, but the good thing is that this polynomial has integral coefficients. And the proof is basically the same also on the number of edges. One can write a very easy recursive formula. And hence, to answer problem now, we can just give a sequence of integers for a given graph G, and the sequence of integers will tell us how many colorings of the graph there are. Okay, so this was combinatorics. Now let's do statistics. I am not a statistician, but I do know some statisticians, and they often are interested in the following problem. They make observations, and observations have an outcome. Let's say they choose a vector in R2. So maybe they measure weight and height of certain animals, and this we can consider as a vector in R2. And this I would call the data. And we collect a lot of data. We can imagine a lot of points, let's say in R2 or in Rn. So what do we do with the data? Well, we try to fit a statistical model that would explain best where our data comes from. And what do I mean by a statistical model? I simply mean a family of probability distributions. And one such very famous family of probability distributions are Gaussian distribution. I think many of you should know from mathematical studies one-dimensional Gaussian distribution, which is this bell-shaped distribution. But there are higher dimensional analogs of those distributions where, for example, in dimension 2, we should imagine such bell-shaped distribution. And what determines the distribution in higher dimensions? Well, it's of course, as in one dimension, the mean, which is now the vector, but how this bell is spread and in which direction is governed by a symmetric positive definite matrix, which is the analog of variance in one dimension. And in statistics, determining a model, let's say a multivariate Gaussian model, is determining what kind of symmetric matrices we would like to take. And in this talk, I will be interested in so-called linear concentration Gaussian multivariate models, where our space of matrices, linear space of symmetric matrices, will be fixed, or even more precisely, we will fix where, in which linear space the inverse of the symmetric matrix belongs to. Okay, so we fixed some space of symmetric matrices that we allow for our model, but what's the problem here? Where is the integer? I see there is something in the chat. Is this a question? No, so it's still the same slide. So it's the second slide. Where I discussed second point. Okay, so so here the problem is as follows. When I am given a data, I can ask, given the symmetric matrix, what is the probability of observing this data, or more precisely, what is the value of the distribution function on that data? And I would like to maximize it with respect to the matrix. This is called maximum likelihood estimation. And the unique matrix that maximizes this maximum likelihood is our best guess where the data comes from. And how do we do that? Well, we could compute the partial derivatives of the product of the function evaluated at the data. And we could look where the partial derivatives vanish. So certainly the maximum will have this property, but the number of critical points might be bigger. So we can have some complex critical points. And the number of those is somehow the measure how complicated our model is. And it's known as the maximum likelihood degree. And that's an integer, the number of critical points in this setting. Okay, so we had combinatorics, we had statistics. Now let me describe one more problem that I like. We could have a nice variety, and what I mean here by a variety, it will be a very special variety. I take a square matrix where entries are linear functions, yeah, so something like 2x plus y minus z, every entry is of that form, and I take the determinant, and I look where it vanishes. So I look which matrices are degenerate in that space of linear matrices. Well, this is a variety, so it's a topological something, but it's certainly not a number. So how do we extract a number in topology? Well, there is this well-known Euler characteristic, which associates, let's say, here not only to a manifold but also to a variety, an integer, maybe not positive. And we could ask, for example, for Euler characteristic of degenerate matrices in our linear space. This would be a number that tells us something about this space. And last problem that I would like to describe, so we had currently combinatoric statistics topology, and the last one I would like to describe is in enumerative geometry. Here I will work always over complex numbers, and Pn is an n-dimensional projective space, complex space. And I pick there A general points and B general hyperplanes. And I can ask the following counting problem. How many quadrics, so degree 2 homogeneous polynomials, pass their zeros, pass through the points and are tangent to the given hyperplanes? Some of those problems are quite old, like the problem about chromatic polynomials, and this one, they are certainly well over 100 years old. In this last one, the answer in algebraic geometry goes under the name characteristic numbers. And it certainly appeared in the fundamental work by Schubert in the 19th century. Okay, so these problems, there is always something given. There is always an answer, which is either an integer or a sequence of integers. But these problems are for very different areas of mathematics. They are quite classical, but from very different areas. So what is this talk about? Well, this talk has one aim only, namely, I will be trying to persuade you that all these problems, and in fact, even more problems, including something called the algebraic degree of semi-definite programming. If there will be a question what is it and how it's related, I will be happy to explain it. So semi-definite programming here comes from optimization, which is yet another branch of mathematics, very popular now. And I claim all these problems are just one and the same problem. Okay, they seem very different, but I claim there is one universal construction and one counting problem, and all of those problems I described so far are simply shadows of that one problem. Okay, and I find it very interesting, and I'm very excited about this. So first of all, maybe the main reason why I believe this is interesting is that you can now translate one problem, let's say from statistics or from combinatorics, to this other language, let's say of enumerative geometry. And there you can apply quite powerful non-trivial theorems from cohomology to get some features of the problem you started from. Okay, now the second thing is that while these are shadows of the same problems, you see, sometimes we got a sequence of numbers, sometimes we got just one number. So I hope that this unified approach can give like a new point of view on those numbers in every single field. The last one is that because not all of the numbers appear in every single field, we can introduce new invariants, new important numbers in those fields where we already know, for example, in combinatorics, we got a sequence of numbers. So basically in every single other field, we should get a sequence of numbers, but maybe ML degree was just one number. So those other numbers should also have meaning and be interesting invariants. And last but not least, we actually gain new effective implemented on a computer methods to compute those numbers, and new theoretical methods to actually compute those numbers, not only use some theory to say certain features of those numbers, but actually compute them. Now, often when I hear people building a unifying theory between like many fields, this theory tends to be super complicated, and you might be slightly scared that on the next slide, the object that will appear will consist of a 5-tuple, a graph, a matrix with linear entries, a quadric, and something like that. Don't be worried. In some sense, this universal construction might be the easiest one of all that I described so far. So I think this is also a big advantage that this unified construction, it's not getting more complicated. Okay, so I said all these problems, there was something given. Sometimes it was a graph, sometimes a statistical model, sometimes a linear space of matrices, sometimes the number of quadrics. But I claim what is actually given is a linear space of n by n matrices. I claim that in every single instance, what was given was a linear space of square matrices. For people who like tensors, you can also say that a tensor is given. Okay. Now, at this point, you can say, oh, come on, you're lying. Your first example was a graph, and the graph is not a linear space of n by n matrices. So let me tell you why a graph is a linear space of n by n matrices. So first, I built just one matrix, adjacency matrix of a graph, in the following way. First, I orient the graph in an arbitrary way. It doesn't matter how I orient it. And now I build a matrix with rows and columns indexed by vertices and edges. And basically every edge gives me just a sequence where everything is 0. There is only 1, 1, and 1 minus 1. Namely, there is a 1 from the vertex from which it's outgoing, and minus 1 to the vertex to which it is incoming. Okay, so this is one matrix. It's not a square matrix. It doesn't have to be a square matrix, and it's not a space of matrices, but this is just one matrix. And the row span of this matrix is a subspace of a vector space C to E. This goes under a representation of a graphic matroid for people who like matroids. Yeah, so I somehow encoded my graph as a subspace of a vector space with distinguished bases. This is simply C to the number of edges. Well, still not a space of n by n matrices, but I claim that in this special instance, we will just have diagonal matrices, and I should look at my C to E as space of n-dimensional space. So let's say that small n is the number of edges, and I claim that my space C to E is the space of diagonal matrices. And now the row span of M happens to be a subspace of diagonal matrices. And this is what I claim should be given in problem number 1 about chromatic polynomial of a graph. Any questions to this slide? Okay, so let me maybe make an example. Where
yes.
Yes, please.
Can you please repeat why this matrix would be a diagonal matrix?
No, so I make it. So I just get a subspace of C to E. Maybe I can follow it here on this example. So I take a 6 by 6. I take a 6 cycle. So the first adjacency matrix, it's absolutely not a diagonal matrix. Yeah, it looks like something like this. Is this fine? Yeah, this is not a diagonal matrix. Okay.
Yes. Okay.
Okay, and now I take its row span. So this is a subspace of C6. It's still nothing to do with diagonal matrices. It's a subspace. It's a 5-dimensional subspace of C6, namely the subspace given by the equation that the coordinates sum up to 0. Okay, and only the last part. It's only the last part where diagonal matrices come in. Namely, I identify my C6 with the space of 6 by 6 diagonal matrices. Okay, and now my space of subspace of C6 where the coordinates summed up to 0 gets translated to the subspace of diagonal traceless matrices. Okay, so from a 6 cycle, I get traceless diagonal 6 by 6 matrices, and this is a 5-dimensional space of traceless 6 by 6 diagonal matrices. Is this fine? Hello?
Yeah.
Yes.
Okay.
Yes, it's fine.
Okay, perfect. Okay. Now, in one of the constructions, there were, and a very important one in enumerative geometry, there were A general points and B general hyperplanes in Pn. And how is this a space of matrices? It completely doesn't look like a space of matrices. So please remember that symmetric n+1 by n+1 matrices, well, they clearly form a space of certain dimension, namely n+2 choose 2. And we can identify degree 2 polynomials in n+1 variables, homogeneous degree 2 polynomials in n+1 variables with symmetric n+1 times n+1 matrices. Namely, if we are given a symmetric matrix and we want to change it to a degree 2 polynomial, we just multiply it from left and right by a vector made of indeterminates. Okay, now every single condition, either passing through a point on tangent to or being tangent to a hyperplane, decreases the dimension of the space of symmetric matrices. In other words, unless a plus b is equal to n plus 2 choose 2 minus 1, we will not get a finite number. So if a plus b will be smaller than this number, the answer will be there are infinitely many quadrics satisfying this condition. And if a plus b will be greater than this number, then the answer will be there are no quadratic polynomials satisfying this condition. So up to scaling, everything up to scaling, because we are in a projective space. So in fact, notice that we don't need to know a, b, and n. It's enough to know a and n, because there is only one meaningful b for which there is an answer is a finite number. And each of a points gives us, so if we look at degree 2 polynomials that pass through a given point, this is a linear condition on the symmetric matrix. Yeah, if you take a symmetric matrix where the entries are indeterminates, if you multiply it from right and left by a given vector, you get a linear equation in the entries of the matrix. So in other words, degree 2 polynomials that pass through a given point, they form a linear space of symmetric matrices. And I claim that these A points give exactly the linear space of symmetric matrices that should be the correct input to our problem. Okay, so at this point, my hope is that I persuaded you that in every single instance, what could be given is maybe not a graph, maybe not a, b, and n numbers, but it's a space of matrices. It's just, the only thing is what changes is that sometimes it's a space of symmetric matrices, sometimes it's a space of general matrices, sometimes of diagonal, but it's always a space of matrices that is of fundamental importance in those problems. Okay, but this is only what is given. Now, we always ask for something. Sometimes we ask for chromatic polynomials, sometimes how many quadrics satisfy certain thing. And as I said, I claim there is only one problem. Okay, so I somehow have to translate all of those problems into one problem that will just depend on a linear space of matrices. And this comes now. We have our linear space L of matrices. And well, whenever we deal with square matrices, there is one very important polynomial, the determinant. Okay, and I take this determinant f and I take its gradient. Okay, so the gradient is a map from my space L to Cn square, because I have n by n matrices, so I can differentiate with respect to n square variables. Okay, so I get, on the level of projective spaces, I get a so-called rational map, because it's not defined everywhere. The gradient might have zeros precisely on the on matrices of rank at most n-2. The gradient will vanish and I will not be able to go to the projective space. But apart from that, let's say on full rank matrices, I get a well-defined gradient map from PL to PCN square. And I claim that my problem, this thing that I am counting, will only depend on that one map. Well, that's slightly a lie, because actually there are two related constructions. So note that when I take a gradient, I can do two things, because my space L is a subspace of n by n matrices. I can take the gradient of the determinant, or I can take the gradient of the determinant restricted to PL. The difference is that once I restrict the determinant to PL, I can only differentiate it in directions from my space L. So I am going to a smaller projective space, PL dual. But you can just think about the first map where to a matrix, I associate the gradient of the determinant. If you don't like the gradient of the determinant, this is the same as inverting the matrix, this map. Or because we are in a projective space, it's also the same as taking the adjugate matrix. So n minus 1 by n minus 1 minors of my n by n matrix. Okay, well, this is not a number or a sequence of numbers, but this map has a graph. So pairs something in the domain and the image of this thing. This graph lives in the product of projective spaces, the domain times the codomain. And I claim that all of the questions I asked so far in this talk, they are about the multi-degree of this graph. And at this point, I should explain what's the multi-degree, okay? So when, as said, by training I'm an algebraic geometer, and algebraic geometers study varieties. What is a variety? It's a zero locus of polynomials. So you have a lot of polynomials and you look at their common solutions. If you are given a variety in a projective space, there are two major, very important invariants of this variety. One is what is its dimension, and the other one is what is the degree of the variety. So let me explain what's the degree of the variety. You have a variety and you cut it with a hyperplane, a random general, we say hyperplane. Well, the dimension, the variety loses dimension by 1. And you continue until at some point you get dimension 0, which means just some number of points. And how many points you get is called the degree of a variety, a very important invariant. Now, if your variety is in a product of two projective spaces, you cannot ask for the degree because you do not have a distinguished hyperplane. Yeah. In fact, you have two hyperplanes. You can take a hyperplane in PL times whole PCN square, or you could take whole PL times a hyperplane in PCN square. And these are two distinct objects. You should not identify them. One of them, let me call H1. The second one, let me call H2. So what can I do with my variety that sits in a product of projective spaces? I could intersect it with various representative of H1 until I get points, and then I get one number. But I could also intersect it with representative with H1 until I get something of dimension 1, a curve, and then intersect it with H2. And I will get a different, in general, amount of points. So I get a second integer. I could also intersect it with H1s until I get something of dimension 2, and then intersect twice with H2. And I get a third integer. And so on until I just intersect with various representatives of H2. So what I get is now not one integer, which corresponds to the degree. I get a so-called multi-degree, which is a sequence of integers. Is this clear? Any questions?
Mateusz, would it be possible for you to give a particular example for it? So
yes,
that
yes,
I
yes.
do understand. Yeah.
Yes. So I do have more complicated examples coming later, but
Okay.
maybe let me do an easy example. Let's try to do some easy example to see what's going on. Let me try to. So let me take P1 times P2. Okay. A product of two projective spaces. Yeah. And I can take something very simple, namely I can take P1 times a point. Which is here. Okay. Okay.
Okay.
Now the two hyperplanes here are of the type point times P1, that this is what I was calling H1, okay? And P1 times P1, this is what I was calling H2, okay?
Mhm.
Okay, now what happens when I will intersect this and this? When I intersect these two varieties, what happens?
So I got point.
Yeah, you
Proper
got
point.
1 point, which is a point times a point.
Yeah.
And that's your first number, 1. Okay. But
Okay.
what happens when you intersect this and this?
I will get the same P1
No,
times
no,
one.
because in this P2, this point
Yeah.
and this P1 will not meet.
Ah, okay.
So you will get an empty set, which is 0 points.
Why don't they meet?
Well, because I take a general P1. I always assume oh, sorry, I did it wrongly. So this was a point times P2, and this was a P1 times P1. So this is my H1.
Mm-hmm.
I take a hyperplane here, which is just a point. The hyperplane in P1 is a point, and everything here. And then I take
P1.
everything on the first thing and the random hyperplane on the second coordinate. So if I fix a point in P2, and if I take a general P1, they will not meet. So I will get an empty set. So in this example, my multi-degree will be 1, 0. Okay. And you can play it with any variety. You will get dimension of the variety plus 1 many numbers. And you see they are not equal.
And how to view it graphically? The multi-degree of the graph, you are saying?
Well, so this graph is it sits here, and we just have to start intersecting it with those hyperplanes from the left. There is a comment, for example, in Macaulay 2 that does it algebraically and returns you this multi-degrees. There are beautiful papers by Alufi that tell you how to do it using characteristic classes and Segre classes. There are very recent algebraic works by people like Yaron Sidruiz, who also give features of this. This is related to many different branches, but I give a very easy definition, but it's not very practical one, really cutting this and counting how many points you get. Yeah. But there is an analog of Hilbert polynomial that would tell you what are those coefficients that I somehow don't mention and maybe slightly hide under the rug here. Okay. So I claim all of those problems are about this multi-degree. Okay. And when you want to join a few disciplines, the good thing is that usually strong people already worked in those areas before you. So these theorems, it's funny, they were not phrased in the language I have just given. So they are not about linear spaces of matrices, but you can just very simply translate deep, hard, strong results from by various people to this setting. And you can say that Jun Ha, who just got Fields Medal 2 months ago, one of his main results was that this multi-degree that I just described are so-called signed coefficients of the reduced chromatic polynomial. Okay. Now you can go to the work of Sturmfels and Euler, who basically prove. So I have these two constructions, so I get two sequences of numbers, but they say that in statistics, the last number in the sequence of numbers is very important, and one is a so-called degree of the statistical model, and the other one is the maximum likelihood degree of the model. So this number of critical points. And you can go to great mathematicians like Tessier, who was studying singularity theory, and again didn't care really about the setting that I'm described. But in one of his really fundamental papers, he proved that when L is general, then both constructions give the same numbers. Okay, and if you go to the work of Joan, you can also rephrase it by saying that for diagonal matrices, both constructions give the same numbers. So when L is general or diagonal, you don't have to make a distinction. You can just focus. It doesn't matter if you restrict the determinant or not. Okay, and if you go to the classical work of Schubert, this is how it actually all started. He was the first one to realize that the multi-degree solves the problem of counting quadrics that pass through points and are tangent to hyperplanes. Any questions about this?
Okay, what John who have done, it was done in some other theory.
Well, so because he was working with diagonal matrices, he never talked about matrices, and he just talked about the affine space Cn. And you know, if you have a diagonal matrix, the determinant is just the product of coordinates. So he was working with the gradient of the product of coordinates. He never called it the gradient of the determinant. But you know, it's a very simple rephrasing. And then actually this example that I have on the next slide is very much in Junha type of theory. So we go back to our cycle, okay? We go back to our cycle example. So you can compute the chromatic polynomial there. You will see that this is k minus 1 to the 6 plus k minus 1. You can check it. That's an easy combinatorial exercise. I didn't tell you what's a reduced chromatic polynomial. Well, if your graph has an edge, the chromatic polynomial always have a root at 1. You cannot color it with one color properly. So the reduced chromatic polynomial is just a division of the chromatic polynomial by k minus 1. And this is the polynomial you get. You see, this is this k to the 5th minus 5k to the 4 and so on and so on. Okay. And I claim that what June proved is that the coefficients, the absolute values of the coefficients of this polynomial is the multi-degree of the graph that takes a traceless 6 by 6 diagonal matrix and associates to it its inverse. Okay, so in particular, if you take all traceless 6 by 6 matrices and if you invert them, you will get a variety of certain, now not diagonal, well, still diagonal, but not a linear space of 6 by 6 diagonal matrices. And this will be a hypersurface of degree 5. And this degree 5 is one entry of the multi-degree, and it's one entry in the reduced chromatic polynomial. And what June did after he realized this theorem, he took deep theorems from cohomology theory and started to use them to prove what properties these coefficients must have. Okay.
By traceless matrices, you mean the matrices with trace 0?
With trace 0, yes. This comes from the fact that the linear span of this adjacency matrix was the whole space, but with the condition that coordinates sum up to 0. Okay. This is how we got the traceless matrix from the 6th cycle. Okay, any questions about that? I mean, if you want to know, for example, what's the 10, this is what you would have to do. You have to take your 6 by 6 traceless diagonal matrices, and you have to intersect them with a general hyperplane. Okay, so this will be now a codimension 2 linear space. Then you invert all matrices from that space, and you get a variety of degree 10. And that's another entry of your multi-degree. Okay, and all of those entries, they give you coefficients of the chromatic polynomial. Okay, so this is, I would say, the main part of the talk. So if there are questions, that's absolutely the main part. It's a good part here. But I also wanted to say a few things about methods, because it's not that we only translated and realized that good people before us were doing pretty similar things. We have very good deep methods to study those numbers.
Mateusz, he did it for the C6 cycle, right?
No, he did it for any graph. This is just an example of a 6 cycle.
Okay.
This works for absolutely any graph.
Okay.
This works.
Yeah, the graph should be the directed one, right?
Well, it doesn't matter how you direct it. You can direct it, and the answer is the same no matter how you direct it.
Yeah. Okay.
Okay. So I wanted to tell you that in algebraic geometry, we can go back to exactly the question that you already asked, like how to compute this multi-degree, I mean, of the graph. What is it geometrically? How do you really intersect with those hyperplanes? And there is an intersection theory that could answer it, but it's bad idea to do it directly because this graph could be very singular. And what actually is the correct thing to do is to resolve the singularities of this graph to make it smooth. And this is what you do. You take n by n matrices, and there is a procedure in algebraic geometry to replace some bad set by a big codimension 1 set known as the blow-up. And you consecutively blow up rank 1, rank 2, rank 3, up to rank n-2 matrices. And depending whether at the first you had diagonal, symmetric, skew-symmetric, or general matrices, you get very beautiful varieties. In case of diagonal matrices, you will get the permutahedral variety. If you watch Juni Haas Fields Medal YouTube movie, he will start drawing something on the board, and this will be the three-dimensional permutahedral variety. Okay, but for symmetric matrices, you get an equally beautiful variety of complete quadrics and so on. For general, you get a variety of complete collineations. And on those smooth varieties, you should do intersection theory. So this is a picture I made for symmetric matrices. So S2V means the space of symmetric matrices. Downstairs, we have a map from the space of symmetric matrices to the space of symmetric matrices. This is just inverting the matrix or taking the adjugate matrix or taking the gradient of determinant. It doesn't matter. Then we have a graph of this map, which lives in the product. And then upstairs, we have a variety of complete quadrics. This is a very beautiful variety that could be considered as the resolution of singularities of the graph. And how do you construct it? I wanted to give you an idea because it's a very powerful and yet an easy method. Yeah. So you start by taking a symmetric n by n matrix, and first you remember it. You remember just the matrix. Then you remember all 2 by 2 minors of this matrix. Then you remember all 3 by 3 minors of this matrix. Then you remember 4 by 4 up to n-1 by n-1 matrix. Yeah, so you get those long vectors. So you get really a map from symmetric matrices to a much bigger space. And the closure of the image is exactly the variety of complete quadrics. That's also a variety studied now for about 100 years by many people. And it has 2 types of distinguished codimension 1 varieties in it. One is that because it lives in this big product of projective spaces, we can just take a hyperplane in one of those projective spaces, and we could intersect our variety with that. And this class of divisors, they are called Li, where I tells you in which hyperplane you are taking the product. And the other one, SIs, they come from this blow-up construction. So they are called the exceptional divisors. What actually Schubert, without having all of those theories, and I don't know how he did that, he was a genius, realized is that the problem of counting quadrics that pass through points and are tangent to the given number of hyperplanes is nothing else than solving this intersection problem. So here product denotes intersection. You just have to intersect a few times divisor L1 and a few times divisor Ln-1 and count how many points you get. And not only did he realize that was more or less obvious that this is the correct counting problem, he also provided very good tools to do that. Namely, he said how to pass from one set divisors to the others. And then he said that the formula for our counting problem is actually given by this, which looks much more complicated because now there are these Li's and Si's. But he also says why this is simpler, because once you are on an Si, you can use combinatorics and geometry of the Grassmannian to solve it. And I didn't want to spend too much time on this geometry of Grassmannians, how it goes, but let me say algebraically what kind of numbers are actually very important, and they are called Laskow coefficients. So what you have to do is you have to take complete homogeneous polynomial, but not in variables, but in sums of variables. So I take a degree 2 complete homogeneous polynomial, so a sum of all monomials of degree 2, and I evaluate it at 2x1, x1 plus x2, 2x2. And then I have to write it as this is the complete homogeneous polynomial in 2 variables, and this is called so-called elementary symmetric polynomial in 2 variables. And the coefficients I get are the coefficients I need to answer the counting problems that I have described. And why is this? So those Laskow coefficients, they are given by phi I. They've been studied again by many famous mathematicians, including Pragach, Laksov, Laskow, Torap. After Laskow, they are named. And you can restate, again, not in this language, because the variety of complete quadrics, I think, doesn't appear in the work of Bottmer and Randstadt. But if you take their deep result and put it in this setting, you will see that what they say is that this intersection number we are interested in is quite explicitly given in terms of Laskow coefficients. So this allowed us to prove some open conjectures by Sturmfels and Euler, for example, that this counting function, which also coincides with ML degree function for general linear concentration model, this is a polynomial in N if you fix D. So this is how those polynomials look like. Before our work, they were only known up to degree 4. So this is the case of symmetric matrices. If you put them in a table, you get a table like that. If you did exactly the same table, but for diagonal matrices, you would get the Pascal triangle. So switching from diagonal matrices to symmetric matrices, you can say that this is like a version of a Pascal triangle. And our result tells us that if you read it column-wise, you get a polynomial. And we also obtained very efficient tools to compute those polynomials. I will give you one of those polynomials in just a second. Now, let me say that those results, they have a very down-to-earth basic consequences in very basic geometry. Okay, so you can ask how many quadrics, so degree 2 homogeneous polynomials in n variables, pass through D general points and are tangent to the correct number of general hyperplanes. So our result can be interpreted that if you fix D and vary n, then this is a polynomial in N. So maybe you heard about log concavity results by Junha so Junha result would be for diagonal matrices, and this would be row-wise. Row-wise, this is just a finite sequence with zeros, and classical Hodge theory gives you log concavity of this sequence. We go column-wise, and we obtain a polynomiality result, not only for diagonal matrices, but for all of those types. Yeah, these polynomials, they look like this. So this is an example for 17, and you can say, oh, they are really horrible. But there is some magic here that I still don't understand. If you look at the coefficients, they look log concave. So if you take module and logarithms, they look concave. And this is absolutely unknown because, you know, June was able to apply all this Hodge theory, which also would translate to this case row-wise. But this is when you fix a variety, you fix the dimension. And what we do is like we vary the dimension, and yet we get some shadows of log concavity, which is very amazing for me. And I have no idea, well, is it true in general, or is there some theory that could explain it? Well, so you can say that our results are about symmetric, skew-symmetric, and general matrices, which would be type A, C, and D. We also proved a few other conjectures, like Nierannstadt-Sturmfels conjecture about algebraic degree of semi-definite programming. There are also ways to upgrade these formulas from just numbers to saying that these numbers are sums of dimensions of certain representations of groups. But unfortunately, lifting this up to the representation theoretic setting seems to overcomplicate problems. And basically, in my whole talk, I was mostly concentrating on general subspaces. Of course, in practice, one is often interested in special subspaces. The story goes through, but it's technically more involved. And recently, with Rodi Kadinu and Martin Wodyczka, we managed to prove a conjecture also by Sturmfels and Euler for the degree of a so-called graphical cyclic Gaussian model. I think there are a lot of future directions to follow, like this log concavity that I mentioned. There is a very nice basic result. We take a space of matrices of fixed rank I, we cut it with a space of fixed dimension, and we ask for the degree of a so-called dual variety. Again, some polynomiality results are expected, but it's still open in general. We could change the cohomology class with which intersect. We again would expect polynomiality result. Now, Jun's work is very much about matroids, and these diagonal matrices basically give the whole theory of matroids. The question is, can we somehow do the non-commutative, so let's say symmetric matrices theory of matroids through the cohomology of complete quadrics? And of course, the question is about applications further to statistics and other graphical Gaussian models. Thank you very much.
Thank you very much, Mateusz. Thank you for very elaborated talk, and definitely touching many high notes in the area of enumerative combinatorics, and particularly the work of John Hu and all big names. So any questions from the audience? So please go ahead and ask. Anyone?
Maybe meanwhile people would be thinking, let me make an advertisement. So here at the University of Konstanz, we are trying to get very good master students. So if you would be interested in coming for us, but also bachelor studies, but master students in master program is in English, so there should be no problem. So anyone who would be interested to coming for us for master studies is very much welcome.
Yeah, wonderful. So lots of opportunities, and okay, lots of results. So today we have with us another university who joined us today is Qaid-e-Azam University, which is one of the oldest universities in Pakistan. And you can, Mateusz, you can see the conference hall there. Lots of participants who are attending this talk. Thank you very much, Dr. Tariq and Dr. Tayyab and Dr. Maria and their team for joining us. And Mateusz, I just, can you go back to that polynomial you have shown toward the end of your talk?
Yes.
Log concave one. Yeah.
So log concavity basically means that if you forget what are the numbers, but just look how long they are, they grow longer, and then shorter.
Yeah. I just out of my curiosity, because when we talk about the H vector, F vector in the for simplicial complexes, so most of the time we are concerned with the positive coefficients there and the log concavity, and here there are negative.
Yes, but this is like for the chromatic polynomial, we just take module.
Ah, okay.
But by the way, to be honest, for chromatic polynomial, the alternation of signs is quite easy. While in this case, I'm not sure if it's not only a conjecture.
Okay. And secondly, there is no easy way to look. You started with graph. So there's no easy way to look at the graph and computed attack approaching to this particular point by using only the combinatorics coming from the graph, or everything is with the help of the matrices.
Yeah, so first of all, so the graph will only give very special diagonal matrices.
Matrices, yeah.
Spaces,
Okay.
very special spaces of diagonal matrices. So even not all spaces of diagonal matrices. So of course, if we are dealing from a subspace coming from a graph, then probably looking back at the combinatorics of the graph would be helpful. But already for symmetric matrices, there is no chance like that, or at least we do not know yet the combinatorial object, and it probably doesn't exist. That would be the counterpart of the graph.
And,
yet the counterparts
yeah.
of chromatic polynomials, for example, exist.
But by looking at the particular graph, how would we know that there would be some singularity coming, and then we have to introduce the blowups, what you was using there?
Yeah, so let me say it this way. If you just want to do counting for one graph, certainly combinatorics of the graph is the easiest. And maybe you also, even if you want to do it for algebraic geometry, maybe you shouldn't resolve the singularities. You should really just intersect the graph. The problem is if you want to apply high-level theorems in cohomology theory. They work best when your variety is smooth. And if you have bad singularities, you may have troubles. So if you want to have not explicit results, but qualitative results, like log concavity, yeah? It's not a result, what is the number, but just that they satisfy something. So this log concavity is just positive definiteness of certain minors. So you need some positive definite results, but they best work if you're in a smooth setting. Now, at least, okay, it doesn't have to be that what you intersect is smooth, but you would like to have a nice smooth ambient space. And this permutohedral variety in the setting of June and the variety of complete quadrics in our setting was actually super important. And it somehow doing nice mathematics also guides you how to solve the problem. If you do not do the resolution of singularities, you will not see those two types of divisors, LIs and SIs. But once you do it, you have them and you can use them. So this resolution of singularities is not necessary. I know it looks like an over-complexifying thing, but it's actually to simplify things. It's used to simplify things.
I missed that part where you was trying to explain the role of Grassmannian. So Grassmannian, what kind of role they are playing in this particular setup?
Yeah, that's a very good question. So this map, okay, it's not defined if you take a low rank matrix, because if you take a matrix of rank I, and if you start looking at I+3 minors, you will get 0, 0, 0, and it's not an element of the projective space. Okay, so this map, so you have to somehow close the image. The image of this map is not closed. You have to take the closure of the image. And now the question is, what are those points that you don't get in the image, but you get in the closure? So they basically correspond to low rank matrices, but over every single low rank matrix, you get a lot of things, not just one thing, because this closure is big. And this is this divisor Sj. If you look at all matrices of rank J, this is very similar to a product bundle over a Grassmannian. So a symmetric matrix of rank J, it's had an image which has dimension J and gives you a point in the Grassmannian J G gen N. Yeah. Because the image of a matrix is a point in the Grassmannian. And it turns out that over that one matrix, the whole fiber in the variety of complete quadrics looks like a product of two projective spaces. One is the second symmetric power of the universal bundle. One is the second symmetric power of the quotient bundle over the Grassmannian. And this is why these divisor SJs are nicer than anything else, because you can move from moving intersection theory on SJ to making intersection theory on a Grassmannian. And intersection theory on a Grassmannian is combinatorics. It's something well understood thanks to 100 years of work of great people. Young diagrams, Shure, and so on.
Yeah. Oh, thank you. Thank you very much for these elaborations. Now there appear a question. Hania, over to you. Go ahead, Hania.
Yeah, hello. Thank you for a very nice talk and for remaining down to earth as much as it was possible. I just wanted to confirm if I got the point right. So basically all these are problems in the different that you recounted in graph in the combinatorial one, the one in topology using the Euler characteristic, determinantal variety, and so on. These are shadows of the classical enumerative geometry problem. Is that right?
That is true. That is true, with one exception, that if we go to general matrices, well, it's also maybe less classical enumerative problem. I don't know if Schubert. No, I think Schubert already also even studied it. Yes, so that's completely right. Yeah.
Okay. So so you said that basically in your basically in your setting, these integers come as sequences like the multi-degree. Is that right?
That is absolutely correct.
So in your setting, how I mean, I'm not sure where to see the cohomology theories that you're using as your method embedded in your setting. Is it easy to point that out?
That's a good question. So if you look at the cohomology ring, let's say let's focus on the symmetric case, because it's the case that already gets out of the combinatorial case of graphs, but it's still very much down to earth. So this variety of complete quadrics, which might look quite difficult, but as I say, it's a simplification. It has its own cohomology ring, and this ring is, I would say, quite well understood. And it turns out that, let's say, these numbers that we have here, every single number that appears on this page is certain computation in the cohomology rings of complete quadrics. So very precisely, if I fix a row here, this row fixes one variety of complete quadrics, and it has its own cohomology ring. And in that ring, if I do certain multiplications, I will get a number, and these are those numbers. And these numbers, they have interpretation in those different branches of science. But what makes it actually the most powerful tool is that these numbers are exactly coming from computations in the cohomology ring of the variety of complete quadrics. I don't know if this answers the question, or yes, maybe I can do better.
Yes, it does. Thank you. Thank you for
so particularly you are talking about the cohomology, algebraic cohomology one, the local cohomology, right?
No, so this is the classical topological cohomology ring, which, because these varieties are so nice, it coincides with whatever you may know else, which could be a Chow ring. Yeah, so Chow ring, cohomology ring, they are all the same in this setting.
No, I got it. Thank you. Thank you.
And the cap product in cohomology is just the intersection in the Chow ring. And yeah, the grading is basically the same.
Yeah, thank you. Thank you. Any other question from the audience or comment toward the end of the seminar? Thank you very much, Mateusz, for accepting our invitation and selecting a very good topic and very excited talk. Very excited talk. Thank you very much. Thank you everyone for joining us, and hope to see you once again. Next speaker of the John Conway Spirited Seminar Series is Professor Ari Laptev, who is an analysis expert from Imperial College London, and he remained the president of European Mathematical Society and editor-in-chief of Acta Mathematica for a very, very long time. So he's going to talk about something related to operators in our next seminar. Once again, thank you, Mateusz, for taking time. And
thank you very much. It was a great pleasure.
I hope some students will definitely apply in your university for master's program. Many students will be, so all interested students are encouraged to do consider this opportunity. Thank
Thank
you.
you a lot.
Thank you. Thank you. Bye bye.
Thank you. Goodbye.
Goodbye. Allah Hafiz.